Nice job.
Now we will miss the first example, alas.
I'm very proud of you for that.
Well,
So I believe this would just be, let me think of this. I believe that you would need 5 minus 3/10 or 15, excuse me. 5, yeah, 5 minus 3/10, and on the right side, 5 plus 3/10.
plus 3/10. Okay, let's... I think we might have multiplied instead
I went
of...
that the wrong way around.
Yeah, because we want to go... To go up, we would multiply by 3, because that would go from x to f of x, which is 3x. So if we multiplied by 3, this would go up to
Yeah.
9/10, right?
So that would go to, instead of 3/10, that would be 1/30th, and, well, minus 1/30th, and on the other side, 5 plus 1/30th.
Good, good, good. Okay, so we see that if x is within this slightly narrower range, so now rather than just 1/10, we have to narrow slightly, just because of the slope of the line. If x is within that range of 5, that will guarantee the target output is within the tolerance of 1/10 within 15. Okay, so I don't know how much your algebra class emphasized this, but is it intuitively clear that this inequality is the same as writing the absolute value of x minus 5 is less than 1/30th? Is that totally obvious, or would you need an intermediate step to verify that these two are the same?
We went over this very briefly.
Okay. Uh, let's maybe see why that's true then. So let me just draw a number line and say here's 5. So the whole idea here is that if you're above 5, if you're some distance, I don't know, delta to the right of 5, then the absolute value of, let's see, if this, yeah, so if x is 5 plus delta, so let me write it this way. So delta will be the distance to the right of 5, and x is going to be delta plus 5. So if x is on the right side of 5, then the absolute value of x minus 5, well, here x is greater than 5, so this is going to be a positive number inside the absolute value. So that will simply give us delta, a positive value to the left. If, on the other hand, x is to the left of 5, and say this is some different value, x equals, I don't know, 5 minus, say, Greek letter lambda, then in this case, we would have x minus 5 is going to be the absolute value of now minus lambda, because x is 5 minus lambda, so 5 minus lambda minus 5 is minus lambda, but the absolute value of negative lambda is positive lambda. So in general, whenever you want to describe the distance between a given point and a number like 5, but you don't care whether the distance is to the right or the left, you can wrap it in absolute value signs, because as we've just seen, if the number of interest x is to the right of 5, then this absolute value is going to give you the positive number delta, which describes that distance to the right. But if instead x is to the left of 5, it's 5 minus lambda, then this expression, absolute value of x minus 5, will again give you the positive distance that x lies to the left of 5. Is that all clear?
Yep.
Okay. So let me ask you a question then. If I wanted... Do I have an extra slide for this, perhaps? Ah, good. I gave myself an extra slide. Okay. So if I wanted to say that the variable... So say the variable y is within some distance epsilon of 100. How would I write this in a single line using an absolute value?
So that would be the absolute value of y minus 100 is less than epsilon.
Good, yeah. So it's always of the form absolute value of variable of interest, the base point, the point that we're measuring the distance from, a less than or less than equal, and the tolerance. So distance epsilon. Perfect. Okay, so in this language using absolute values, so what did we just say in the previous slide? What did we say? Well, it was that if the absolute value of x minus 5 is less than 1/30th, then that implies what was f of x? F of x was 3x, will be within a distance of 1/10 from the target value 15. So now that I've written it this way, it's almost stupidly obvious, right? Because the whole thing we've just demonstrated is equivalent to taking this expression and multiplying by 3, right? Since if you simply multiply this whole thing, the left and right side, by 3, on the left side you can move the 3 inside the absolute value and distribute to get 3x minus 15. And on the right side, 3 times the 1/30th is 1/10. So this line thing that we did was really just multiplying by the slope on either side. So are we happy with that step?
Yes.
Good, okay. So all we're doing right now is getting intuition for how to make points on a line close to a target value. Okay, so in the previous example we've had this 1/10 floating around. So now we're just going to generalize. It doesn't have to be 1/10. It can be any positive number epsilon. So now let epsilon be any positive real, epsilon greater than 0. And now I'll ask you, how close does x have to be to a particular value here, a equals 5? So what distance does x need to be to 5 for f of a, which is 3a, to be within that tolerance epsilon of 15? Or in other words, what inequality for x do I need in order to get this inequality for f of x? What do you think?
I missed something.
Okay, so let's back up and see what the other example was. So in this example I said, the question before was how close does x have to be to 5 in order to make sure f of x is within 1/10 of 15. So now all I've done in changing the question is replaced this 1/10 by a different number epsilon. Right? So this question was, how close does x have to be to 5 for f of x to be within 1/10 of 15? Now I'm asking a different question. How close does x have to be to 5 for f of x to be within epsilon of 15? Same question, 1/10 replaced by epsilon. So walk me, if you don't see it, walk me through what your brain does when you try to parse the question. Which part are you tripping on?
I believe that this would just wait. Give me a sec to think about this.
Maybe I should remind that this is still 3x.
I believe what we would need is the absolute value of 3x minus 45.
Let's see.
No, I don't know.
3x minus, okay, well, why don't we do what we did before and divide both sides by 3, right? So this is how we got from the 1/10 to 1/30th, right? So f of x is 3x, so I think if we have this bound, that x minus 5 is less than epsilon over 3, then the first line will be true, right? So this is simply, maybe I should draw a picture to make it totally clear what we're doing. So the line is this 3x, which, I mean, just have to be somewhat generous with that slope, pretending that's actually 3. So here's 5. So if this is the point x equals 5, and these 2 points are 5 plus some positive number epsilon over 3, and 5 minus that same epsilon over 3. We're trying to see how close does that range get us to 15. And I think what we've just shown by multiplying by a third, that gets us within this bound between 15 plus epsilon, and this one down here is 15 minus epsilon.
Okay, I thought we were going the, well, opposite way compared to the previous problem, so I got confused.
Okay. Yeah, maybe I should have made it. I guess you could, since here it's just algebra, in principle you could go in either direction, but we like to think of it as starting with the output, f of x, with a prescribed tolerance, and then going backwards to x, the input, and ask what tolerance does the input need. Okay, so is this step, are we happy with this now that to get this we need this?
Yep.
Okay. Who's interesting. Alright, so Corbin has disappeared. Whoa, what is this? I don't want that. Alright, again I give us an extra slide for this, which was apparently not necessary. I should have used, right, I could have drawn that picture larger on the next slide, but I didn't. Okay, so let's go over here. So now we're going to generalize one more time. In the previous examples, we were asking specifically about the point 5, and now I'm going to be smarter and use an entire slide to draw. So we have the same function. So here we're going to still be thinking about 3x, but now I'm saying consider any real number a. So I don't know, a could be negative or something. And we're going to ask how close x has to be. So we're asking for this range in x in order to get a given tolerance around f of x. So here this is 3a, right? So now if this epsilon is given again, it's going to be the same question. So suppose you really want to ensure that the y value, the output, is going to, oh, this is actually plus, oops, 3a plus epsilon, since that's above, you want to ensure that it lies in this interval from 3a minus epsilon to 3a plus epsilon. So my question to you then is, in this case, for any a and epsilon, how close does x have to be to a for f of x, which is 3a, to be within epsilon of this target?
I believe that this would be the absolute, second speech. I believe that this would be the absolute value of 3x minus a is less than epsilon.
Wait, did you say 3x minus a?
Yes.
3x minus a is less than epsilon. So this is telling us that 3x is within epsilon of a. I'm confused. Okay, so hold on. This is, so here's 3x. No, sorry. What are we saying here? Here's a, and you're telling me 3x lies somewhere in here. I don't think this is quite what we want. So the question is, if we want, so 3x minus, maybe this is what you were saying, this is the desired outcome, right? So this is the statement I've drawn in pink here, right? This is the statement that 3x is within epsilon of 3a. And then what is the range, what does the absolute value of x minus a have to be to guarantee this? Or in other words, how close must 3x be to a? which is this blue interval here. Basically, how much wiggle room do I have for x about a to guarantee that it hits this target?
Well, I don't have any other answer for that except for epsilon. Just
So
epsilon. So I'm done. This is so simple. I don't know where I'm getting confused.
okay, I mean, so if the line had slope 1, you're saying that if x is within epsilon of a, then it'll hit this target. And maybe that's just because I've drawn the line a little poorly. If the line had slope 1, that would be true. So what did you just claim? Let's just write it down. So you just claimed that if x is within distance epsilon of a, which is this inequality, you claimed it will be true, I'll put a question mark, it will be true that 3x will be within distance epsilon of 3a. I don't think this is true, though. I don't think it's true that if we have this guaranteed, then the second line will necessarily be true. Do you see why?
Well, yeah.
Yeah, right. So, for instance, if x is a plus 1, and, I don't know, epsilon is 1.5, then it's certainly true that 1 is less than 1.5, but it's not true that 3 times 1 is less than 1.5. Right. Maybe I should make the geometric intuition clear. Oops.
Have you at this point already given me the answer? I don't know.
I don't think I've said it directly. Why, do you want to take another crack?
I just couldn't tell.
Okay. Well, should I draw it again more explicitly, or do you want to talk, walk me through your thinking?
I'm just gonna think.
Okay. Maybe I'll just put a line here for what the question is. So the question is, how close does x have to be to a? X minus a is less than question mark, which would guarantee this.
That would be epsilon over 3.
Yes, good. So,
Okay. Are we doing the same problem 3 times?
yeah, we've been changing one thing each. First it was a equals 5, then we got rid of, first it was a equals 5 and epsilon is a tenth, then we changed 5 to a, and then we changed 1/10 to epsilon, so this is the third one. So it has been getting slightly more general, but I don't know, often people find this extraordinarily confusing. Like, I'll write down this definition and people act like it's the hardest thing they've ever seen. So most textbooks go very slowly through introducing this. I don't know why. Is this all relatively clear, or is it hopelessly confusing?
Is the A that we're using... Wait, no. Let me think. What is A?
Any real number. The point is that this argument applies regardless of the value of a. Right? So if you prefer, you can think of this entire argument as wrapped with a quantifier for all a. This is true. But if you pick any particular value of a, this argument goes through. Okay, so
Not how what we're doing now is different from other... Well, what's the proper name? I guess interval of some sort?
interval of some sort. Okay, maybe just since it's important, I want to see what the apparent takeaway is. So can you explain back to me what it is that we're doing in this example?
It would seem that wow, my brain just died there. I'm getting that. Yeah, I'm getting nothing. I'm getting that epsilon is how close that we want to be, and that's about it.
Okay, yeah, let me draw the motivation again, because remember, this is all about our goal was to capture the idea that a function gets close to a particular value at a given point. And we're trying to show that if a function has that property that it gets close to a particular value, like 15 or 3a, then we can encode that behavior by saying that the output gets arbitrarily close to the target, like 15, by guaranteeing the input is arbitrarily close to the limit point, like 5. So more specifically, let me use one of these empty slides. So all that we're doing in these 3 examples is making the following argument more and more general, that if you have the line, which for us was like 3x, but I mean, you could let this be any line you want. So I'll try to, that's not very good. I'm trying to make this a little steeper than before to make it clear. This is very steep. So suppose someone comes along and hands you a particular tolerance. They say, this is your job. Here is a particular value 3a. You're allowed to pick any constraints on the input we feed this function you like. But after you pick those constraints, you had better guarantee that whatever number this function outputs, it's going to lie between these 2 bounds, this upper bound and this lower bound. And the upper bound is 3a plus epsilon, and the lower bound is 3a minus epsilon. So the question we're trying to solve is Q, how to guarantee that it lies in that bound, right? How to guarantee f of x lies in this interval, which is 3a minus epsilon, 3a plus epsilon. Okay, so is the statement of the question clear?
I believe so.
Okay.
I'm getting hooked up with the 3a and the numbers in it.
The 3a and the number, like the
I'm getting hooked up on the 3 and how we're handling that. That's all.
Oh, I see. So the choice of the slope 3 and how that's appearing in our answer basically is confusing.
I guess so.
Okay. Maybe it'll be clearer when we do another example, because here the only thing 3 is doing basically is telling us that to answer this question we have to realize that this line has slope 3, so our error is going to get multiplied by 3, right? So this is the answer to the question, that since we get to choose any constraints on the input to the function we want, if this is a, and we know that if we have a small error, like if we feed into this function something which is not quite a, but it's a minus epsilon over 3, that error gets multiplied. If we feed in a minus epsilon over 3 to the function 3x, the output, you just multiply by 3, it's going to be 3a minus epsilon. And likewise, if you feed in something which is again not quite a, but it's too big, a plus epsilon over 3, your error of epsilon over 3 gets multiplied, because when you apply the function 3x to this, you multiply a by 3, you multiply 3 epsilon by 3, and that gives you this value. So the answer to the question, how to guarantee f of x lies in this interval between 3a plus epsilon and 3a minus epsilon, answer, we choose x in the smaller interval, a minus epsilon over 3, a plus epsilon over 3. And then
I'm not even sure I'm confused anymore. If I don't know if I was confused before and I just didn't get what the question was asking.
okay. So now it's clear where, because you mentioned 3 was confusing before. Is it clear why 3 appears in the answer now because of this slope?
Yes.
Okay.
I know what's going on.
Good, good. I mean, this is it seems very simple, but it's important that your understanding goes all the way through to the bottom. So, I mean, be wary of where all these numbers are coming from. If we replace this line with 5x, then of course this would be a minus epsilon over 5 and a plus epsilon over 5. Okay. So why are we doing all this? So, good. So I just argued that you could run this same argument with any epsilon and any point A. Actually, maybe it's clearer, just the picture that I just drew makes this even clearer. So we can make the output as close as we would like to 3a, any positive epsilon. We can guarantee it's going to be that close to the output by choosing a particular range of values that are allowed inputs. So this is what we mean by the statement that the function gets close to 3a. So remember, the first thing I said that our goal for this entire procedure is to rigorously quantify the statement. So I guess here's the non-rigorous statement. The function f of x equals 3x gets close. I'm putting gets close in scare quotes because that has no mathematical meaning. Gets close to 15 near x equals 5. So this was our problem we were trying to solve. Our problem was to take this sentence, which is meaningless because these are just English words. We wanted to give this mathematical meaning, the statement that 3x gets close to 15 near x equals 5. And that's what I've tried to do in this slide, is to show you what I mean by getting close is that if you hand me any tolerance, you say you must be within this closeness of 3a. I can guarantee that for you by giving you a corresponding closeness, a nearness, if you will, a nearness of x equals 5. Okay, so thoughts on whether, we haven't quite gotten the definition yet, but thoughts on the direction we're taking to rigorize this statement?
I have no thoughts. I think I understand this.
Okay, good.
I'm trying to learn how to write on a computer. It's painful.
Oh, have to draw for tomorrow?
Sure. I'm just trying to get good at kind of taking notes at the same not trying to get good at taking notes, just trying to write an idea.
I see.
I'm not even explaining my own right.
I think I understand what you're saying. So you're saying I'm trying to take notes with a tablet and I'm trying to understand what are the things I'm supposed to write down or what ideas I'm supposed to capture, right?
I really don't like writing.
Man, is it better or worse than using paper and pen, though?
I have no idea.
Yeah, alright. Okay, so this is our first proof of calculus. This is the first thing which I think actually counts as a calculus result and not, I don't know, set theory or something. And since we're putting on big boy pants now, I'm going to start distinguishing. Before, every time we proved something, I called it a theorem. In math, you normally use different words to communicate how important the result is. So you reserve the word theorem for the most important results, like the Pythagorean theorem or something. Smaller, less important results you typically call propositions. So this is just a specific example for 3x, so I'm going to call it a proposition. And this will be our model for how the rest of the proofs, like we're going to be writing many epsilon delta proofs, so this is kind of a prototype for what they look like, and it's just an extension of what we saw in the picture. So here's the statement of the proposition. Let f of x equal 3x, that's the function we're talking about, and let a be any real number. So that's kind of the base point, the limit point in the previous drawing. So those are the assumptions. Here's the conclusion. Then the limit as x approaches a of f of x equals f of a, which here happens to be 3a. So what is this saying? To prove this, we have to go back and use the definition of the limit. Because, of course, any proof is really just the statement that a particular definition is satisfied. So you have to use the precise statement of that definition. So to prove the limit exists, we have to show that for any epsilon greater than 0, there's a delta so that if x is within delta of a, f of x is within epsilon of L, which here we've picked a value of L, which is 3a. So this is the definition we have to use. Now let's look at the proof. So these epsilon delta proofs will almost always start with a statement like, let epsilon greater than 0 be given. And why is that? That's because in the definition we just saw, the statement was that given an epsilon, there exists this backwards e, a delta. So that means that to prove the limit exists, all I have to do is show you that if you hand me some epsilon, I can cook up a delta that has the required properties. So you can think of it as a game. Someone who doesn't want the limit to exist is going to try to pick an epsilon that's really hard, and he's going to hand it to you, and you need to just describe a strategy to always get an appropriate delta that will work. So to do that, you start by saying, all right, let epsilon greater than 0 be given. Now I have to tell you what delta to pick. You told me a moment ago that if I want that output to be within epsilon of the target, all I have to do is choose x to be within epsilon over 3 of a. So this is delta. The thing that the bound for x, the distance for x, is the Greek letter delta. So in my proof then, I'll say, if you hand me an epsilon, I will simply choose this value of delta. Delta equals epsilon over 3. Now we're almost done. Just need to explain why that works. So if x is within a distance delta of a, which is written like this with absolute values, absolute value of x minus a is less than delta, which I've defined as epsilon over 3, then here's a conclusion. And whenever we're reading a proof, we should understand, if I make a conclusion, why is that true? So it's an algebraic reason, but if the first statement is true, can you tell me why this deduction is valid?
Well, this is just a case of multiplying by 3.
Yeah, good. So simply multiplying both sides by 3 kills the epsilon over 3 to epsilon and moves the 3 inside to give us 3x minus 3.
Okay, so as I'm understanding it, x or if it has coefficient random number x, that's just this effectively function that you're operating on. A is the point that you're operating on. Epsilon is basically the output tolerance, and delta is the input tolerance.
Yes, that's all we're doing. To prove any limit exists, all you have to do is say, if you hand me an output tolerance, I can cook up an input tolerance. Exactly. So since this, after you've said that, basically, that's the only line in the proof which is non-trivial. So this line is basically just saying if x is within the input tolerance, then the function f of x is within the output tolerance. Here that's clear just because it's multiplying by 3. And then that's it. That's the proof. So notice that to do this, I mean, this is kind of another example of exploration versus argument, because we had to go through several slides of drawing pictures to understand what is the right delta to choose. That was all the exploration. Once you've figured out what delta to choose, the proof is always like maybe a paragraph, a couple of lines, because you just say what the delta is and then you're done. So you usually have to do these kind of proofs in 2 steps. One where you cook up the delta, and then 2 where you write out the proof. Okay, so you just summarized this, so I think you understand it, but other questions or thoughts on this thing?
I have no questions. Wonder when Corbin's going to be back.
He did say that he's disappearing because his audio's glitching. I don't know. Shame.
Oh, he might be gone until he does stuff, so that could be not now.
Could be forever. Okay, here's another way I like to visualize it. You probably noticed I always like Python analogs. So what was the whole point of this? So our game is kind of like defining a function. So you could think of these proofs as cooking up a function which I call get delta, and your function takes in epsilon. So epsilon, the output tolerance, is handed to you. This is the output tolerance. In general, it can also depend on x. In this case, x was given to us, right? Because x equals a was given. So you're allowed to use A in your answer, although we didn't need to. So to write these proofs, all you have to do is basically tell the reader what function do I need in order to get the input tolerance. In this case, it was simple. It was just take the output tolerance and divide it by 3. So all you have to do is cook up this function and then show that it has the required property, that whenever x is within the input tolerance of A, f of x is within the output tolerance of L. Just a different way to think about it. Okay, now let's think about a slightly harder example. So now we're going to look at a parabola. So this is just the simplest upward opening parabola x squared. And near the limit point a equals 3, we expect that the function gets close to 9, right? Since plugging in, I mean, it's not always true that plugging in the value to the function tells you what it gets close to, but it certainly seems to be true in this case, and we'll try to prove it rigorously. So we expect that near x equals 3, x squared gets close to 9. So to prove that, here's our output tolerance statement, right? So our proof will basically be, you hand me some epsilon, and I need to guarantee that the function, which is x squared, is within that tolerance epsilon of 9. And to do that, I have to make x close to 3. Okay. So I'm going to do the exploration again, since this part is slightly more involved. So we're trying to think about, all right, if x minus 3 absolute value is small, how do I get this to be small? So one thing you might think to do is like, well, this thing is one of the factors of this like quadratic absolute value. So you might start by saying, let's try to factor it. And if we do that, we factor the statement that we want, which is that absolute value of x minus 9 is less than epsilon, which is saying x squared is within epsilon of 9. If you factor that, you get these two pieces. So the product of these two factors we want to be less than epsilon. One of these we can make small very easily, because we are allowed to choose any delta we want so that x minus 3 is less than delta, right? That's the game. We get to choose delta around the input value of 3. Last time, let me ask you, so in the last problem, this factor of x plus 3 was a constant. What did we have? What factor replaced absolute value of x plus 3 in the previous example?
I don't believe I remember or understand what is being asked.
Okay, the previous example was the line, and this thing was just the slope 3, right? So in that example, we had 3 times the thing we are allowed to make small was less than epsilon, right? Do you see what I'm saying, or is it?
Yeah.
Okay. So what's different between the previous example and this example is that now it's not a constant, right? This is this thing x plus 3. So that factor is annoying. We're going to have to do two things. First, we're going to restrict the values of x that we consider. So we're allowed to pick any range of x's that we want. And we're going to try to do it in such a way that we can bound this term. We want to convert this to some constant. We want to get a worst case bound on this. So here's what I'll suggest. Since we're ultimately going to make x very close to 3, let's start by assuming x is within 1 of 3. Right? So if we assume this, if x is within 1 of 3, it must be true that 2 is less than x is less than 4. So let's assume that. If we've assumed that 2 is less than x is less than 4, now what is the biggest that this annoying factor, absolute value of x plus 3, could possibly be? What is the upper bound for absolute value of x plus 3, assuming x lies in this interval?
I believe this would be, give me a sec. I just had it in mind. don't believe I am answering this the right way, but I believe that the value that you would put here would be 7.
Yeah, that's totally right. Yeah, the biggest that could possibly be is 7. I mean, the smallest it could be, let's see, if we plug in 2, we get 5. If we plug in 3, we get 6. Plug in 4, we get 7. We know x is bounded above by 7, so this is x is bounded above by 4, so the absolute value of x plus 3 is bounded above by 7. Very good. So that helps us out, because if we look back at the pink line, we're trying to bound this product, and now we know one of them is upper bounded by 7. So now I'm going to use that in the next line. So if we've restricted the values of x we're considering to 2 is less than x is less than 4, which means absolute value of x minus 3 is less than 1, now we can replace that annoying factor, absolute value of x plus 3, in this product by 7, since we know this is bounded above by 7. So that means the statement we want to prove, the statement we want to guarantee by choosing x appropriately is that the absolute value of x minus 3 is less than epsilon over 7. This is what we want. Now we're basically done. Because remember the game. The game is that you hand me an epsilon, and I get to pick a delta with the property x minus 3 is less than delta, right? Delta is the input tolerance, and x is the input, and 3 is the point about which the tolerance is assessed. So I get to pick any value of delta I want, and make this true. So if I want this, then I can get it by just choosing delta equals epsilon over 7. Right? Because if delta is less than epsilon over 7, x is within that distance of 3, which is what I want. The only thing we have to be slightly careful about is what if epsilon is a big number? What if epsilon's like 14? Then epsilon over 7 would be 2, but back in the first step, we started by saying, well, we're going to restrict to values where x is within a distance 1 of 3. So we really mean to take epsilon over 7 if it's smaller than 1, and then take 1 if epsilon over 7 is bigger than 1. So to be totally correct, what I should say is the value of delta that I pick is the minimum of the two numbers 1 and epsilon over 7. So this is delta that I'm choosing. Okay, so that's a lot of steps. Ask me questions on this.
So it would seem that what we did here was we factored and handled each individually. Am I seeing this correctly?
Yeah, we factored to x plus 3, x minus 3. We identified one of those as the thing which we are allowed to bound by choosing delta. The second one it seemed like we had no control over, so we made an additional assumption and used that to get some control over this extra factor. And the price we paid for that extra assumption was writing our answer for delta in terms of a minimum. Yeah, that's exactly right. Other thoughts?
Have any questions?
Yeah, it's probably a lot to take in, and you might... I mean, I remember the first time I saw this argument, I thought I would not have cooked that up. I would not have figured that out if it were handed to me.
Yeah, I wouldn't be able to, and I probably can't now, so...
Yeah, it's... But after you have seen it a few times and get experience writing these kinds of arguments, it will become very intuitive, in the same sense as when you see... Like, I don't know, maybe the first time when you were in, I don't know, 7th grade or something, when you saw, like, a quadratic, and someone said, well, you should complete the square, and then that's a way to solve it. You would have thought, that sounds crazy. I never would have thought to, add b over 2 squared. That's ridiculous. But now it's very intuitive, since you kind of understand what's going on. So, I mean, I think this sort of argument, where you try to bound one factor to get some control over it, will be much clearer to you as time progresses. It's okay if it's confusing now. Have you ever watched any of the YouTube videos of people interviewing Terry Tao? Have you seen these?
I have no idea who that is, but I like his last name.
He is probably the world's greatest living mathematician. We have a Slack emoji for him, actually. It's just : Tao. I should send you one of those videos, though, because someone asked him, do you ever use metaphors or visual images when proving math? And Terry says something like, sometimes I'm trying to prove an inequality and I need to bound one of the terms or factors in the inequality, and I think of it as though I'm buying something. I think of it with economic intuition. So I wonder whether imposing a particular bound is a good deal or not, right? Like, you make this assumption and the deal you get out is that it's bounded above by 7. Then you wonder, could I get a better deal, like bound that above by 5 or something? I thought it was a very interesting comment. But anyway, so good. So let's just see what that would look like as a proof. So the whole thing we just did was the exploration. This would be the argument. So proposition, the limit as x approaches 3 of the function x squared equals 9. The proof, as always, let epsilon greater than 0 be given. I simply state the value of delta we just cooked up. Delta is the minimum of 1 in epsilon over 7. Then you justify why that gives you the desired output tolerance. Why? Because then if x is within distance delta of 3, we know x plus 3 absolute value is less than 7. It's just by algebra. And that means that the quantity absolute value x squared minus 9, which is the product of these two, has to be bounded above by 7 times epsilon, which is, 7 times the quantity epsilon over 7, which is just epsilon. And this is what you need to prove. You show the output minus the target value is less than epsilon. Okay. Funny story about this proof. This was, I think, the last time, this removed my last shred of, maybe I shouldn't say this because I'm recording it now. I'll say it anyway. This specific problem with that specific limit point removed my last shred of faith in the high school math system. This was at the end of must have been my sophomore year of high school. I was trying to solve this problem, and I was confused about the minimum step, right? I was confused about this step. So I thought, well, Mr. Spurk is purportedly my independent study advisor. Let me go ask him. So I walked to his room, and I had the solution written. I wasn't asking him to solve it. I had the solution written. I said, Mr. Spurk, can you help me understand this step? He stared at it for 5 minutes, said, I don't know what's going on. Then we walked down the hallway and asked every math teacher that was not busy, like Nora Oswald, everyone else, can you explain this step? And they all looked at it and said, nope, I don't know what's going on. So I just went back to sitting by myself and staring at it and thought, like, well, I don't know what I'm doing here. Sad day. All right. Another fun example.
What is that, and why do I like it?
It's pretty weird, right? So this is the function f of x equals x times the sine of 1 over x. So why is this interesting? Definitely this is not defined at x equals 0, because 1 over 0 is undefined. So you can't really see it the way it's drawn, but you should really think of this graph here as having like a little open circle at 0, which is to say we can't plug it in there. But the nice thing about limits is it doesn't matter whether the function is defined at the point. We just ask, what value does it get close to? And just by looking at the graph, we think, well, this is kind of like a sine, but it's multiplied by x, so as x gets close to 0, this is close to 0 times sine, and sine goes between minus 1 and 1, so 0 times a number between minus 1 and 1 should be getting close to 0, right? So our intuition is that this should get close to 0. But as Hardy says, intuition must be held accountable, so we have to prove this. Can we prove that if you hand me any epsilon, I can make this product smaller than epsilon? Is it clear why this is not a product minus a, right? Because here a equals 0. We're trying to prove the limit is 0. So this is really f of x minus L, but L equals 0. Anyway, so how do we prove this thing? That this thing is less than epsilon given some absolute value of x minus delta, where we can pick delta. So we can pick delta. So actually think about this. You might not be able to quite see it, but just think about it for a second. See if you have any thoughts or an idea for delta that makes this work.
It might just be that you can define delta as epsilon over sine of 1 over x. That's a total guess. don't trust anything about.
Well, the problem with this is that this depends on the x value, right? And we're evaluating this close to x equals 0, right? So we can't plug in epsilon over sine 1 over 0, and we can't pick a delta which depends on x, right? We have to pick a number delta which depends on epsilon, right? I think I wrote this confusingly when I wrote the function before.
Perhaps you can take each sign and uh, you may be able to apply arcsine to each side of that. I don't know.
That's good thinking. Yeah, so in principle, yeah, we might be able to make some arguments involving arcsine, but there's actually a simpler solution because one of the tricks of this game is that you don't have to pick the best delta. You could pick any delta which works, right? So we can't do this because it can't depend on the point x. Yeah, I feel bad about writing this now because I really should have emphasized that it can't depend on the point x, but it should really be, it depends on the point that x approaches. So, yeah, sorry, I confused you by saying this. But, okay. Let's see what value of delta works. Let's just let delta be epsilon. Make the simplest choice you could possibly make. So this means we're going to guarantee that the absolute value of x is less than delta. So if it's true that the absolute value of x is less than delta, what happens to this thing that we want to make small? Well, we can factor this into the product of two absolute values, absolute value of x times the absolute value of sine 1 over x. The absolute value of x, we've chosen that to be less than delta, but delta is the same as epsilon, so this thing's always less than epsilon. The sine function gives you a point on the unit circle, and the absolute value of the y-coordinate of a point on the unit circle is always less than 1. So the product of something less than epsilon and something less than 1 is always less than epsilon. Right. So we didn't need to muck around with any arcsine of a particular value because in this game you only need to worry about the worst case scenario. And the worst case for a sine is that it's 1. But we can deal with that by just, picking this factor so that the 1 doesn't kill us. Okay. Is that argument clear about why that goes through?
I'm not entirely sure.
Okay. Let's how can I rewrite this? Okay. Let me just rewrite I have to go somewhere that is not used. Let me just write it a little more carefully with more steps. So we get to pick delta and my pen's screwing up. We get to pick delta so that absolute value of x is always less than delta, and we would like to make that choice in such a way that we're guaranteed that that function, which is x sine 1 over x, sine 1 over x, is less than some epsilon you hand to me. So I'll put a comma where epsilon is given, right? Epsilon greater than 0 is given. So that's our goal. So here's the answer. Suppose that after you give me epsilon, so remember you hand me epsilon, if you hand me epsilon, I'm just going to say, alright, you've told me epsilon is 1 over 100th, I'm going to choose delta to be that same value, delta equals epsilon. Then, so now I'll rewrite that factoring thing. So it's clear that we can always first take absolute value of a product and factor that into the product of the absolute values.
I did not know that that was a thing, quotation marks, a thing that you could do with absolute values.
That's,
So do as much as one would expect.
Well, we can actually prove it. Let's not write it out, but let's just prove it in our heads. So the absolute value says take whatever's inside. If it's positive, return that number. If it's negative, then return -1 times that number. So if we have an absolute value of a product of two things, that's just saying take whatever's inside, make sure it's positive, and return it. If we split that into two pieces, this is saying make sure the first factor is positive, make sure the second factor is positive, and then certainly the product of those two things will have the property that that's going to be positive or 0. So I think
Okay, that's cool.
yeah. Okay. So now we're going to try to bound what this whole thing is, and I'm going to do it in 2 steps. So maybe this isn't clear as well. Has anyone ever told you that there's this rule that if A is less than B and C is less than D, this guarantees that the product, and these are all positive numbers, then it's necessarily true that the product AC is less than the product BD. Is this step clear?
I believe so.
Okay, good. It's good to make sure every step is unassailable, though, right? So if A is smaller than B and C is smaller than D, the product AC should be smaller than the product BD. That's pretty intuitive. Okay. So let's see if we can bound this bad boy. So we have assumed absolute value of x is less than epsilon, which is the same as delta by our choice. So this is less than epsilon times the absolute value of sine 1 over x. Okay. So now, if we're trying to find an upper bound for this product, which holds for any value of x, I think it's enough to just ask what is the maximal value that this function, absolute value of sine 1 over x, could possibly achieve for any value of the input x. The largest value that this could possibly achieve is going to be 1. So is that part clear? That the absolute value of a sine of some number will always be upper bounded by 1?
Yes.
Okay. Good. So if I take the product of two numbers, epsilon and something upper bounded by 1, then that product always has to be upper bounded by epsilon times that bound of 1, which is the same as epsilon. So that part's clear. Or is that the confusing step?
This is like a 50-50.
Ah, okay. Let's see. So, how... I don't know how to draw this. That's used. Fuck. Okay. How about...
Profanity.
What'd you say?
Profanity.
Yeah, I'm trying to think about how to explain this properly. That epsilon is bounded. Okay, so... Okay, well, we're excluding x equals... Is that what you're worried about? That plugging in x equals 0 might give us some strange behavior?
No.
No, okay. Alright, I think I'm stuck. I think you'll have to help me out by talking me through the confusing point, which I know is challenging because by definition confusing things are things that it is difficult to articulate, but I will ask you to try anyway.
I'm gonna say that as soon as you started writing in red, I have no idea where this stuff is coming from.
In red. You mean the lower line here or the step in red here?
Everything in red.
Everything in red. Okay. Let's see. Let's see if we can understand the first step in red. So I claimed that this product is less than epsilon sine 1 over x. So in going from the green step to the red step, all I've done is replace absolute value of x by epsilon. So
Okay.
can you explain why I'm allowed to say that this is less than the same thing with x replaced by epsilon?
Since it is, well, we previously, oh, okay, since I'm being called to explain sound spot, I guess, since x also has a kind of definition that it must be greater than 0 because of the sine function that you have going on there. That's that's literally me just trying to come up with an explanation.
I think that's a reason why this thing all has to be lower bounded by 0, right? Because you're saying this thing, this x, well, really the absolute value of x, that has to be greater than 0, greater than or equal to 0, and the sine has to be, this is an absolute value, so that has to be lower bounded by 0. So I think the explanation you just gave is a good one for why this thing is non-negative. But why are we guaranteed, based on what we've said so far, that absolute value of x is upper bounded by epsilon?
Since I'm going to say that because this is another way of formatting that, well, no. Since epsilon. If you haven't already noticed, my voice gets a lot weirder when I'm confused.
I actually haven't noticed, but thank you. For now I will be even more attentive to that. Is there someone else in the room overhearing you talk about calculus again, which made you nervous before?
No.
Okay, good. It's something. Okay, maybe it would help if I emphasize the kind of input tolerance thing, right? Because here the value of a that we're assessing the tolerance about is 0, right? So remember, the name of the game is that I'm allowed to tell you the input tolerance, which is an interval from minus delta to delta, and then I guarantee, or I am guaranteed after I choose this, that x has to lie in that interval, right? That's how the game works. I get to give you the input tolerance, which is the tolerance for x around 0. So since I get to pick that input tolerance, I made a choice. I said I pick that input tolerance to be epsilon. That was my strategy in this game. So that means x has to lie in this interval from minus epsilon to plus epsilon. So that's guaranteed to me now. That's what I get for my choice. So now can you explain this step in light of that choice?
I don't see the jump that we are making from the absolute value of x to epsilon, but I am understanding that epsilon is, I guess, the tolerance. I don't want to say the limit quotation marks.
Okay. I think I see the issue then. So this is going to seem unrelated, but bear with me for one moment. So how do I write in that absolute value notation? So write an absolute value notation for the sentence x is within, say, 1 of 20. How do I write this in an absolute value?
I believe that you would write this the absolute value of x minus 20 is less than 1.
Good. X minus 20 is less than 1. Now, how would I write, and my pen is screwed up again, write x is within epsilon of 0. How do I write that?
This would be the absolute value of x minus epsilon. Excuse me. Absolute value of x is less than epsilon.
Good. Okay. So if x is within epsilon of 0, the absolute value of x is less than epsilon. Okay. Now what did we assume here? We assumed the input tolerance was that x is within a distance epsilon of 0, and then down here in this step, all I'm saying is that what you just told me, the absolute value of x is less than epsilon. That was this step, this jump here. See, since notice in red there's a less than sign. So all I did was use the absolute value of x is less than epsilon.
Okay, and this absolute value of sine 1 over x is like on both sides, effectively?
Yeah, in this red step, I didn't even touch it. I mean, I put a bracket over it, but I mean, you can always chain inequalities like this and bound piecewise. So I just use this and let the sine 1 over x come through as a spectator. Didn't do anything.
Okay.
Okay, so the first red inequality you are happy with.
Yes.
A hesitation makes me think happy is too strong a term, but at least you are not angry about it. Maybe neutral about it. Okay. What about the second one? The observation that this thing is upper bounded by 1. How are we feeling about that one?
I understand it.
Okay.
Since the greatest value you can get out of the absolute value of sine 1 over x is 1, so that makes sense.
Good. So then, same argument. This is just doing the same thing I just said, where you can chain inequalities and replace one of the terms and bring the other along for a spectator. Right, so if this thing is upper bounded by 1, I bring along the epsilon as a spectator, and then this thing has to be less than epsilon times 1, since I use the 1. So that part's okay, I guess. Or is that part still confusing?
I believe I'm understanding this.
Good, okay. Good. Alright, let's see if we put it all together and see the punchline then. So, what was the whole game here? Someone hands me an epsilon, I have to pick a delta. I said, easy. I pick delta to be the same as your epsilon. And then by using that chain of inequalities that we just showed, if I make that choice, so that absolute value of x is less than epsilon, then this quantity, absolute value of x sine 1 over x, is also less than epsilon. But that's the thing I needed to bound to prove the limit exists. I have to make the function value minus the target, which is 0, less than epsilon. And therefore we've proved the statement which our intuition said was true by looking at the picture, but we've now proved that the limit exists by explicitly describing how to pick delta. Okay, questions on this?
I do have a question.
Good.
Okay. I'm seeing that thus we have shown. Where did we show that?
Maybe I should write the proof more. Actually, no, I didn't write the proof. So we showed it in the step that, let's see, proof. Let me write it more carefully. So if the theorem were that the proposition were that the limit exists, where we showed it is in the following statement. Let epsilon greater than 0 be given. So you say that, and then you have the choice to choose delta. So I say let delta equals epsilon. I'm allowed to refer to epsilon since it was given before. Then here's the step where we show it. We show that the definition of the limit is satisfied. So I know you don't have it memorized yet, but the definition of the limit is that given epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus l is less than epsilon. So to show the limit exists, that long string of word garble, we just have to prove that that's true. And the proof of that statement is this block here, which I'm boxing in orange. So this is where we prove that that sentence is true. So when I claim, thus we have shown this exists, I'm really referring to the statement that with this particular choice of delta, then this statement is true. Is that what you're asking? Was that the question?
I believe so.
Or did you mean something else by where did we show this? Can you unpack perhaps?
I think I don't have any other thoughts or questions, or I don't know.
Okay, but I answered the question at least on what is that what you meant by have we shown it at least?
I believe so.
Okay. You're hedging, which makes me think I didn't totally answer it, but alright, I guess I'll move on. Let's just do some intuitive, since we've done several.
Actually, okay. So it seems like all we proved is that epsilon is greater than 0 overall on all the work that we did there, back on the red and other color, etc.
In this slide, or in the one to the right with the chain inequalities?
In the one to the right, it seems like all we proved is that epsilon is greater than 0.
No, we assumed epsilon is greater than 0. That was not something we proved. Oh, you're comparing the far left side to the far right side. Yeah, I mean, that's not the part of the inequality we're extracting. The part that we're extracting is that this green piece is also less than epsilon. When you have a chain of inequalities, any pair of a left and a right has to be true. So, yeah, this is the part that we proved, that absolute value of x sine 1 over x is less than epsilon.
Okay, now I understand.
Okay, good. I shouldn't have added that extra 0 at the left, I apologize. That was added in after the fact. Good, okay. More questions. This is important, so all questions are productive, I think.
I don't believe I have any questions.
Okay. Good, alright, so let's just do some quick checks. We don't need to write any proofs for these. I just want to see how well the big picture has sunk in. So I've drawn 3 functions, and for some reason I've only labeled the first one. So let's call them f1 of x, f2 of x, and f3 of x. They're all fairly similar in that they're piecewise linear, but f1 of x has this weird discontinuity where it jumps up. So the value of f of x at 0 is 0, but it jumps between 2 values. From the left it approaches something like, I don't know, -1 or whatever, and from the right it approaches 1. So first, what do you think? Does the limit as x approaches 0 of f of x exist for f1 of x?
I believe yes.
Why, yes. Can you explain? What does it equal, first of all? So if the limit exists, it equals a number. So what number does it equal?
I believe that the limit of 1 at... Yes, I'm wording this amazingly. I believe that the limit would be 0.
0. Okay, so you're saying I can make f of x as close as I want to 0 by guaranteeing that x is close to 0. Okay. Can you explain how that's true? So how would you, for instance, if I hand you an epsilon and say f of x has to be within epsilon of 0, how would you choose a delta that makes that true?
I rescind what I said because I cannot explain it.
Okay, which part do you rescind? The value of the limit or whether the limit exists?
I guess both.
Okay, so now you think the limit does not exist.
But haven't we, effectively shown that there exist limits for all functions at like all points technically?
No.
Okay, so
that was the point of the definition, right? The limit, I haven't shown you any counterexamples yet, but the limit only exists if for every epsilon I can find a delta. If that's not true, the limit does not exist.
I don't know anymore.
Okay, let's draw a picture. So if the limit existed, if it were 0 for instance, then let me draw some epsilon bars. So I would have to be able to guarantee that the output of the function lies within this output tolerance of 0. It lies in here when I make x sufficiently close to 0. I don't think that's true though, and here's my counterexample. So say that we pick some input tolerance for x. So x minus 0, which is just x, is less than some delta. This thing is constant on the left side of 0 and constant on the right side of 0. You see, for all positive values, this thing outputs, I don't know, let's call this 1. So for all positive values of x, this thing outputs 1, and for all negative values of x, this thing outputs minus 1. Is that part okay? Or is
I
that,
is
did you say you guess?
what?
What was your answer? You said that was okay, or was not?
Yes.
Yes, okay. So then, let's see. Let's just, for whatever that delta was, let's just say, all right, f1 of delta over 2. So this is within delta of 0, so it's supposed to be within our output tolerance. But we just showed that for any positive input, f1 outputs 1.
Showed.
Yeah, showed. You can say showed or shown. Both are acceptable.
Wait, that's an actual word? Okay, sorry.
Yeah. It's not shoe. Okay, so that one is plus 1, and f1 of minus delta over 2 is minus 1. So it looks like no matter what delta we pick, we're going to get some plus 1s and some minus 1s within our input tolerance. So if epsilon is anything smaller than 1, we can't win, right? We can't make delta small enough because no matter what delta we pick, we're going to get some 1s and some minus 1s. And if epsilon is smaller than 1, these will not lie within the output tolerance, right? You can't get these to lie within some number smaller than 1 of 0. So in this case we say no, the limit does not exist. You can't win the game. No matter what delta you pick, you can't guarantee.
I believe that we did something similar to this. Like, trying to remember the name. It was in the video that had to do with pathologies.
Oh, yes, yeah. I talked about a few things like if a point is removed or if it gets close to some different point, or yeah, I think it was the oscillating one you're thinking of, right? That if I chop it like this or something, then it's going to go outside the range, and I can't get it to be within a set of bars or something. Is that the one you're thinking of?
That's the one that I am thinking of. Specifically, if it's outside of those 2 bars.
Yeah. This is a similar example. In that case, I think it was a limit as it goes to infinity, so I was just drawing things like this forever. But here it's just at a point. It's the same idea, though. The bars won't work. The epsilon bar is smaller than the f bar. I agree. Okay.
Does that same logic apply here, where it's not a limit if you can't really bring the effectively epsilon bars within a certain distance?
Yes. If it's possible to choose your epsilon bars small enough so that you are no longer able to guarantee that the function output lies within that tolerance, then the limit does not exist. That's correct.
Okay, so it would seem by that logic, none of these have a possible limit.
Well, let's think more carefully. So how about f2? So why can't tell me which epsilon bars I can pick. So suppose this is 1 or something. What epsilon bars could I pick so that the output tolerance is not within those bars?
I believe epsilon bars quotation marks that you could get for this would be give me a second to think about this. Just like making it too simple would be, for example, 0 or 2. Yeah.
0 or 2. So the size of the bar is 1, so it goes, you're saying
yeah.
like that, between 0 and 2?
So that would be the absolute value of x minus 1 is less than 1, so epsilon is 1.
Yeah, okay. So you're choosing epsilon equals 1. Okay, so let's play the game. So you hand me epsilon equals 1, and say you have to find a delta so that whenever x is within delta of 0 but not equal to 0, then the output has to lie within these bars. And I say easy. I pick delta equals 1. Done. Why does that work? Because all of the x's that are within 1 of the origin but not equal to 0 lie in here. And all of those x's output a value of 1, which lie between your bars. Right? So I think that works. You see why that works, or is this confusing?
Yes, I think I am seeing why this works.
Okay. Yeah, the point here is that you probably thought, oh, well, you're going to be outside the bars because of this point down here. But if we go back...
You act like it doesn't exist, right?
Right, and why is that true? This is why you have to have every character in a definition memorized. The function f approaches the limit L near a if for every epsilon greater than 0, there's some delta greater than 0, such that for all x, if 0 is less than x minus a is less than delta. Notice this less than. That less than is not a less than equal to. In particular, since it's not a less than equal to, we cannot consider the point x equals a, because if x equals a, the absolute value of x minus a is 0. So that point where the limit point is equal to x is not included in the definition because of that less than, and not a less than equal. So in particular, when we look at that graph of the function and you say, aha, well, at the point x equals 0, you have a problem because it's outside of those epsilon bars that I picked. And I say, no, no, no. The definition says absolute value of x is greater than 0 but not equal to 0. So I don't even have to worry about that point for your epsilon bars. Good. So is that part clear?
Yes.
You sound sullen because of that technicality, but okay, I apologize. But
I don't believe I was stolen. It's just that I'm tired right now for whatever reason, even though I got like 10 hours of sleep.
Okay. Well, we can quit soon if you like. Or we can quit now if you want. Are you tired enough that you want to call it quits?
I'd like to at least finish this part.
Okay. Well, we can finish F3 then. So I claim here the limit does exist, and the proof is actually for any, no matter what epsilon you hand me, I can pick any delta. They don't even have to be equal. The proof is just pick any delta greater than 0 and you're done. Okay, how about F3? Do you think this limit exists?
I believe it does.
Yeah, same thing. Well, not same thing, but you actually have to be a little more careful with picking the delta here. But same technicality that the point doesn't matter because of that less than in the definition. Okay, so we can quit, or I think I have some interesting functions that change values depending on whether f is rational or irrational, like this. And there's...
Oh, Jesus.
Well, yeah. So, what do you want to do those, or do you want to skip and take a nap?
I have no idea. What were our plans for tomorrow's meeting?
For tomorrow, I'd like you to pick some of the solutions to the last few, the harder consolidation document problems. So either the deriving the double angle, the product log, or maybe some of these proofs that you're working on now. Pick like a couple of them that you find most interesting, and then present them with the tablet, the drawing pad, the way that I just did, and be prepared to answer questions, basically.
I think that the one I found most interesting was I can't quite remember its name. Double angle of tangent, I believe. Yeah, it doesn't sound right. Let me try to find it quick.
Oh, double angle of tangent, the tan A plus tan B over 1 plus tan A tan B, that one.
Yeah.
Yeah. That was a sexy formula. Yeah, it's the angle addition formula. I like that one.
Right angle addition. That took me way too long, and I didn't even take long because I technically didn't do it at all, and you just suggested.
Wait, suggested the solution?
Just in the context of me remembering the name.
Oh, I see. Well, I mean, that's fine. There's an asymmetry here because I've seen the problems before and you haven't, so I think it's easier for me to remember them, seeing them my second or third time than you on your first time, so don't worry about it. So what do you think? Other questions about the meeting tomorrow? Or, I mean, if you really want, we could wait and give you more time to finish the other problems and then present like Sunday or Monday, but it's up to you. I don't want to get too far behind.
I don't believe I can do anything on Sunday, at least like Sunday night, because actually taking some time to hang out with friends that people you know, of course.
Ah, good. Okay, that sounds fun. So the week after that, so like Monday, not Tuesday, because you're running, Wednesday and stuff. Will you have time to work those days, or do you have other engagements?
Um, I forget what the calendar for Scotland was like.
What's in 11 days from now, right? Or 10 days now?
Yeah, 10 days. So yeah, that's plenty of time. Never mind. So no, that doesn't bother me at all. This week or the first 2 days of the week after that. I don't know. I'm trying to remember this
Okay, so
until the week after next week on Monday.
right.
Trying to remember stuff right now.
Sounds like you have a lot of things to keep straight in your head.
Even though it's really just Scotland and cross country practicing.
Well, I'm sure. Whoa, there's a screenshot here that I wasn't aware of. No, I'm sure there's other things you have to keep straight in your head that are outside of that list, but I mean, perhaps aren't relevant. But okay, so how about why don't we plan to finish as much of the consolidation document as possible by the meeting tomorrow? Present whichever things you find interesting. Then Sunday you'll be busy, but then if necessary, we take Monday as a catch-up day to like really finish the document, make sure everything's correct and totally right, and like put it on GitHub and stuff, and then keep plowing through limits. Like, I guess we'll meet Wednesday then next week.
Yes, I like this plan.
Okay, good. Other questions about the consolidation document problems? Anything you're stuck on and wanted to talk through?
Perhaps we could discuss 7.7 a bit more, specifically the entire idea of algebraic number.
Yeah, okay.
Because yeah, still having problems with it.
Good. You can always ask for help sooner. I don't want things to be too painful, but it seems like I don't know if it's prideful or just you don't want to like be a burden or something, but it seems like you avoid asking for help until a long time has passed. Okay, so this is the stuff so far for algebraic numbers. Okay, so let's recall the definition. What is an algebraic number? So we say x is an algebraic number. That's a bad algebraic A. It's like this, but with an extra. If there exist integers a0 dot 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 an, so that this equation holds. So the constant integer a0 plus a1x plus dot 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 plus an x to the n equals 0. So a number a number x is algebraic if, to prove it's algebraic, I have to explicitly hand you all these numbers. I need to say, all right, here's the integers that appear as coefficients in my polynomial, and the number x is a root of that polynomial. So for instance, let's do an example. So proposition, say, I don't know, square root 3 is algebraic, right? So how do I prove this? Well, how do you prove anything? You look at the definition and show that the definition is satisfied. So it's algebraic if there are integers with the property that a was 0 up to an xn equals 0. I get to pick n, right? Because this is just a list of n integers, so I can pick whatever n that I want that works. So proof, let's see, what n do I want? Well, why don't I just say for I think I only need a second order, so I'll say for n equals 2. And what coefficients do I need? Well, let's see. Let's let a2 equals 1. So that means the thing in front of the x squared will be 1. And I get to pick the constant term. It has to be an integer. a0 equals minus 3. The polynomial is... Well, what's the polynomial? Well, it's x squared. Oh, I should have said there's one more a. I forgot. a1. Let's pick that to 0 so we want no linear term. So x squared minus 3 equals 0. So that's the polynomial I cooked up. But square root of 3 is a root of that polynomial, right? So, but square root of 3 is a root of this. So because square root of 3 is a root of a polynomial a0 plus a1x plus a2x squared, where I got to pick all of the a's, that means by definition square root of 3 belongs to the algebraics box. Okay, so there's an example. Questions or clarifying things about the definition or the example?
So do you just have to show that there is one polynomial where it is a possible root, or it to show at all that it is algebraic?
Yeah, because here's the definition. If there exist, right? It doesn't say how many there have to be. This is an existential quantifier. There exist. So to prove that there exists something, I just need to show you that there's at least one. If there exists one, then the definition is satisfied.
Okay, so it doesn't need to be true for every single degree up to infinity.
No, I mean, you can prove that there are. Once you have 1 degree picked, you can keep cooking up more, but you don't need to. That was, I mean, maybe I confused you by putting that example in the statement of the problem where I said, hey, look, 1 is algebraic, and then I showed that you can cook up higher and higher degrees. But that wasn't necessary. That was just an illustration. For the definition, you just have to show that there's some polynomial of any degree that you want.
Okay, this makes so much more sense.
Okay, so is it clear why this proof for square root of 2 doesn't work? What's wrong with writing down this polynomial and saying, hey, here's my polynomial where all the a's are integers?
Since the square root of 2 is not a integer.
Yeah, so mapping onto the definition, you say a0 is root 2, and a1 is 1. So the 1 is fine, the a0 equals root 2 is not fine. So that one doesn't work as a proof for root 2.
Okay, I have a question. Do the imaginary numbers and do imaginary numbers and integers overlap at all?
No. So integers are only the real 1, 2, 3, and the negative ones. So negative 1, blah, blah, blah. So this is, yeah.
So for that reason, 2i is not algebraic?
I think I is still algebraic. I don't need the coefficients to be imaginary for the root to be imaginary. Here's a simple example.
Okay.
X squared plus 1 equals 0. See, 1 is an integer, 1 is an integer, but I is a root of this, right?
Okay, so once again, this is just that there's a degree where I is a root.
Yeah, just to cook up one example, single polynomial. Here I plug in I, and it's a root.
Okay, so this is making more sense. Cool.
Good, okay. Questions about B or C for that, or the bonus? Or do you want to give us a try first?
I'll give it a try first.
Okay, good. Yeah, I apologize, this one's confusing, but this problem is mostly an exercise in reading definitions carefully, right? Because as you've seen with delta epsilon, that thing is very information dense, right? The definition carries so much data, and if you miss one bit of that data, your proofs will be wrong. And this this problem is very similar because the definition of algebraic number is also very dense. There exist integers. Those three words carry the information that you only need one polynomial. The statement there exist means there's just one. The integers a0, that contains a lot of data as well, since it rules out the proof that root 2 is, it rules out this one where you used root 2 as one of the integers. It's very dense. So anyway, yeah, I know it's a pain to have such a high attention to detail where one single word can completely screw over the meaning of the sentence, but everything that we do from now on is going to have that property. So you have to get into the habit of reading with a magnifying glass and making sure that every single preposition makes sense to you before starting the proof.
So you have to read English like you would as if you're checking code.
Yeah, I think that's a very
Oh
good
boy, that can go terribly.
Yeah, that's all proofs are, right? Proofs are using English words in a way which is as logically precise as computer language. That's right. That's why when you wrote proofs of set equality, it all boiled down to the properties of the words and and or. And you would have said like, well, and or are just English words. No, they're not English words. I mean, in math, and is a very precisely defined operator with like a truth table, right? So by and, I don't mean the English word and, I literally just mean this truth table.